So if you know that the curves were a single parameter equation, that's x equal to x of u, y equals y of u, and so on, that we saw in the morning. And then we saw some curves on the, cubic spline, then the Bezier. Okay, we use the p of t there, which is x of t, y of t, and z of t. So these notations are here and there. We use t, we use u, then uv, uw, all those notations will come because each book has its own notation, and when we pick from that book, we kind of follow that notation. But of course, we can use any letter there as long as we understand that they represent the parameters. So, but a parametric surface, as you can see here, it will be two parameters. So we can see if you have a curve, if you have a point and move it in a space in a single direction or a single parameter, then it will be a curve. And if you do the same thing and if you move in a kind of two different directions, you generate a surface. So that is the rough idea of two parameters and one parameter. So this will become u direction, and this will become, sometimes it is w, sometimes it is v. We use t, phi all over the place. So this is the basic idea of a parametric surface. Okay, this is of course in 3 dimensions, and there are special cases on that, and we will see that. So what we are very important to understand is called as a surface patch. Okay, the surface is sometimes also as a surface patch. What is the meaning of a surface patch? Okay, so we can see here is that we use the notation. Basically, this is P00. If you are not able to clearly see, that means the U value is 0 and W value is 0. And if you travel along this curve, and you can see that the P value becomes, U value becomes 1, and then W is still 0. Okay, remember this is the kind of U and W direction. Okay. So in a similar way, so we can see that this is P of 1, 0 at the end of the curve. And then similarly, you can have along the travel direction, if you do it, you can see that this will be U equal to 0 here, and he will use the notation P 0 and W becomes 1. Okay, see, remember this is the W direction, or if you want, you can imagine like this also. Okay, so in a sense, what I'm trying to show, this point, the corner point of the last one, both u equals 1 and w equals 1. Okay, but you can observe, so there are how many curves that I have drawn here?
Four curves.
Okay, I have 4 curves. Okay, so 4 curves each belonging to what is called as one constant value in one direction. For example, if you take this curve, okay, which is I'm marking in red, what is the value for u and what is the value for w there? See, remember this is the u direction and this is the w direction. Okay, so what it is varying along this? U is varying. What it is constant?
W.
W is constant. In this particular case, what is the value for W? It is
0.
It is 0. So such curves where you keep one parameter constant and another varying, these are called isoparametric curves. Okay, we use the term isoparametric. You know, iso in many places that you would have used. Okay, iso means constant. Sorry, isoparametric. So here in this case, particular case, as you can see in the red curve, so U is varying and W is 0. Okay, so this is one of the boundary curves. And so if you go for other boundary curves, you can see that in this particular case, U is 0 and W is varying. And similarly here, U is 1 and W is varying. And in the last one at the top, we can see that again, W is constant or U is varying and W is constant. Okay. So we can see that as it varies along this, if you use the notation P of U comma W, right? That is the notation that we are using for this entire surface. Okay, if you put various values for U and V, U and W going from 0 to 1, and then again from 0 to 1, okay, W going from 0 to 1, then you can see that this entire surface will be covered, correct? Yes or no?
Yes.
Yes.
Correct. So that is the P of V comma W. Now, this is one of the boundary curves which I am drawn, let's say the bottom one. Okay, so what is the value of U there? U is varying, right? And W is 0. So we will denote that curve as P of whatever we U as varying. So we can say this is U and then this is 0 because W is 0. Okay, so this curve we will notate it as P of U comma 0. What about this curve at the top? How do you notate it? It is
P of U comma 1.
P of U comma 1. Okay, what about this one? At this level, remember this is the U equal to 0, W is 0. So how do you notate this curve?
0 comma W.
0 comma W, and thereby this becomes P of 1 comma. So you can see that these four boundary curves along with the so-called P of UW gives what is called as a four-sided patch. Remember there are only four boundary curves. So whatever we see in this class actually are all four-sided. Okay. Of course, there are more sides that can come into that becomes more complicated. They are called as trimmed surface patches. So we will probably leave out the trimmed surface patches, but for I think in your possibly in your later classes, they may actually talk more about trimmed surface patches because these four boundaries patches are four-sided patches are little limited. So they go for what are called trimmed surface patches. Okay, I think you may hear that in the tomorrow's class and probably in further classes when they talk about more surfaces on that. So this is very important to understand. So you can see the middle point somewhere here. Okay, that is basically P of Ui comma Wj. So some point along the Ui direction, some point along the Ui direction, and some point along the Wj. So somewhere Ui and somewhere. So this is the Ui comma Wj on the parametric space, and then corresponding point is the mapping point is the P of Ui comma Wj. Okay. So this is basically broadly classified as four-sided patches. So all the surfaces that we will see are going to be four-sided patches. Okay, all that means you have four boundary curves. Okay. Then any doubts on this? All are in shape. So do you guys have any questions on this notation? You can put an yes or no. Is it okay? Then you tell yes. Then we'll just go ahead. Okay, so then we know what is an isoparametric curve. It means one parameter is constant and another is varying. Okay, so this is the on the Cartesian space how this surface is, and of course I talked a little bit about what is called as a parametric space, which is basically a okay, it's not exactly right. So we can say this is an UV space kind of a thing or a UW space. Okay, this notation is not. Okay, you can see this, there's some clumsiness, but there is a W, this is an isoparametric one, W equals Wj, and this is, you can say another isoparametric one, which is, this is on the parametric space. So this will get mapped onto and you generate your P of U comma W after that. Okay, this is always going to be, because this is A is notated, but we'll go with 0, 1 on either side. So this is entire thing is our space for us in the sense. Okay, we map this parametric space of range from 0 to 1 on either side onto the P of UW and we generate different surfaces. So now the whole idea is that as we saw in the curve where you have different mapping functions, like you have a B-spline basis, Bezier basis, and here also we are going to see something on those how you map it, so you generate different surfaces. So that is the idea. So if you go further, so we'll first briefly talk about surface of revolution. Okay, how do you generate surface of revolution? Let's say you want to generate this cylindrical surface. So how do you generate it? So the term surface of revolution. So give me some idea.
So like in circle we had r and theta. So here one more parameters could be.
But we want a surface finally, right? So
Yes.
that
So to
theta
get.
will be,
Sir, we can consider a family of circles which are like translated. Then it will become like a.
but that will still not be a surface, right? Suppose if I translate, take a curve and keep on translating.
It's a
Okay.
continuous translation, sir.
Then how do you connect them?
So they're continuously translated.
Roll it and all. So if you roll it, let's say take a circle and roll it, then let's say something like that, what you are trying to say, then you roll it along. you may get something like this, right? Is that what you are trying to say?
I
Or
I was telling like dragging it, sir.
yeah, so will it create a surface, or it will still be on the same plane? So if you drag a circle and then put a circle and drag it on the same plane, you are only going to get the copies of the circle, right? Something like this. So will that become a surface in
No, sir,
3D?
you drag it in an axis that's perpendicular to the plane.
So drag, can you use a better word than dragging? And dragging is very crude. Anything in terms of transformation, that's what I'm trying to hint at it. You're right, but suppose say you have, okay, you have a, this is, let's say it's an XY plane, right? So now you have a circle. Now tell me, you dragging, what can you say in terms of transformation?
So we can translate it in the Z direction.
Okay, you can translate it in the Z. So if this is Z, then that process is called what? You know that process? Okay, your what background do you have, engineering?
The electrical engineering, sir.
Electrical. Okay, you may have you heard of the term extrusion, extrude?
No, sir.
No. Okay, so basically, if you drag it, which is using your own term, to do that, or somebody has put translation. Okay, then the process is typically called as the extrusion, and more generally, this process is called a sweep. Okay, I mean, we use the term sweep because you are taking, as what you are mentioned, if you're taking and dragging, right? We don't use the word dragging. Instead
Yes,
of
sir.
that, imagine it is sweeping. I mean, more decent term.
Yes.
And dragging is looking very crude. So instead of that, to use the word extrude is also okay, but sweep is a more generic term. Sweep along a curve, along, in this case, it's along an axis. You can do along a curve also. Then it becomes not just extrusion. You can sweep it along some other direction or along a curve and so on. And that is the term. But another thing that you can think of it, what other transformations you can think of it other than dragging?
So to create a cylinder, or are you talking about other shape?
General.
You can do rotations. You can do
Okay, you can do rotation
reflections.
also. So if you take a circle and rotate it about which axis? In this case, if you rotate it about y-axis, what would be the object? Y-axis 360 degrees. So what would be the object?
Spherical.
Hmm?
Spherical.
On. Spherical.
A torus.
Torus. Okay, your vada with a hole. Okay, we have a non-hole vada also. You all of you are fond of vada, sambar vada and dahi vada and so on. So you can see it is a torus. Okay, more technical term is torus. So you will get that. So that are called surface of revolution. So take any plane curve, it need not be a plane curve, but usually examples are easier with a plane curve. Not so you can take a plane curve. For example, if you take a circle and rotate it, you are going to get a torus. But even a simpler case, suppose you take this line and you rotate about this x-axis. What is the object going to be?
A cylinder.
Okay, cylinder. Is it the same as your usual cylinder in the sense, or it's going to be little different? Okay, is it going to be completely closed or not closed?
So it depends on the angle of rotation. If you're rotating one full 360-degree rotation, then it will be a
Closed in that form. Okay, closed in that sense. Okay, I'm talking about closed in the sense of a volume, like whether you have. So if you take this example that is available here, which is exactly, you are right about 360 degree. Okay, so that means is this, but you remember there is this surface is not there.
yes,
The
it will be
top.
hollow.
Yeah, so it will be like a surf. Remember, we are talking about surfaces, okay? That means not solids in that sense. So the internal volume we can still compute here, but we are talking about surface patches, okay? They are not typically actually solids, okay? In our geometric modeling, we have some distinction between the surfaces and then the solids. You can, of course, close the surface also, but that again only we are having points only on the surface, okay? Not on the inside of the thing. So, okay, I'll show you some demonstration. So is this a four-sided patch or not?
So if you have sufficient boundaries, then you can make four-sided patches.
So you have your, these are the values, right? T goes from, let's say, 0 to 1 also you can say, and then phi goes from 0 to 360. So is it four-sided or not? Let's say you go from 0 to, let's say you have this parametric value, this is P of T, let's say it goes from 0 to 1 on T, and then you are rotating phi, right? Phi goes from, let's say, starting with 0 to 360. So now is this a four-sided patch or?
So if I goes from 0 to 360, it will not be four-sided. If it goes from maybe 0 to 90 degrees, then you can have like four sides.
I think it's a two-sided patch because there are only two parameters that you need. Sorry, you will need three parameters. No, two. I think two are enough.
So,
Yeah,
okay, tell me it is 2, 3 or 4 finally.
yeah, two.
See, this is a parameter in T comma phi, okay? I mean, it's same as U comma V or U comma W. Okay, so T has 0 and 1 as boundaries, yes or no?
Yes,
And
Yes,
phi
sir.
has 0 and 360 as boundaries.
yes.
Then how many boundary curves you have?
Okay, only two. But okay, we are not counting the internal circles. Okay, got it. It is only the
But
outermost
0,
circles.
comma 0 and 0, comma 360 won't they be the same point?
So, but how many boundary curves we have? You have not answered this.
Only two. Only two.
Only two, sir.
Why?
So
See, you
because
have... Oh my God.
it completes one full revolution, sir. So it comes back to the same point.
Okay, but still the parameter value is different there, right? Even though you get merging, let us say this guy comes and backs again, and then it becomes, but that parameter value is 360. So you have another blue guy coming in.
So if you can cut it after it comes at 360,
There's no
then you
need to
can.
cut it. Why we should cut it?
So
See,
otherwise we won't get a.
you have two parameters here, you have two parameters. So what are the parametric pairs? You have 0, 0. Okay, and then you have 0, 360, correct?
Yes, sir.
And then you have 1, 0. Okay, so sorry, and then you have 1 comma 360. This is the last one. Is it correct or something wrong? 0, 0, 0, 360.
So I think it should be 1-0, sir.
Okay, 1, 0 and 1, 360. Correct. So you can see that then why should there be only two boundary curves? See, the two
So I
boundary
think
curves get merged. Is correct. But still the parametric values are actually different. Okay, so you have the same four-sided patch, correct? So what happens? This four-sided patch, this boundary is going to get and then get closed here. Okay, correct. That's what is happening.
yes, sir.
But this is a zero parameter on one direction, and this is if this is one, basically instead of, okay, in this case it goes to, let's say, 90 degree this guy, or 360, it will go all the way and it goes at 360 degree on that. So you have another boundary curve here which is actually at a parameter of 360. Yes or
Okay.
no? Right. So this is also a four-sided patches. Okay, even though we don't see all the four sides explicitly, but you can see that phi varies from 0, which is one boundary curve, and then that goes to 360, where the other parameter is going to vary. Then you still have four sides here. Okay, this is still four-sided patch. Okay, if you look at the parameters as such, you still have 430 as a, sorry, 360 as one parameter and 0 as another parameter. So you have a one boundary curve at 0, you have another boundary curve at 360. Okay, in terms of phi. In a similar way, you have 0 and 1s on the other parameters, T of phi or phi T either way. So here also, you actually have, even though we don't see it explicitly, this is also a four-sided patch. Okay. So don't forget that, and that's because we don't see it. That doesn't mean that we don't have kind of a thing. So of course we have several examples, as you people mentioned. Okay, we can have complicated shapes, other transformations. So we can create all these kinds of surfaces of revolution. Okay, so let me just quickly demonstrate some of them. I'll share the other my other screen. So are you guys seeing the screen now with my Okay, you are able to see this. So if you go to the top of the menu, you can see there are lots of surfaces like along with the sphere, cylinder, cone. So you can just click on that. So if you click on that, you can see that, let us say you create a cone. So it is a truncated cone on that. So you can see that you can display the cone or even the cylinder. But if you take a, how do you create this? So do we get this with this approach that we have talked about, or how do you create this? Suppose this is done by surface of revolution. Okay. So do you get something like this or no?
We can take incline lying segment and we can rotate.
So in that case, what will happen? See, there won't be any this top and bar. See, there won't be any top cap and bottom cap. You will see, you have to see something like this, isn't it?
Yes, sir.
Yes, sir.
Right. So if you just take a line, let's say XY line somewhere on this, then if you rotate it, you won't see the closed one. This is actually surface model. Okay, you usually don't put a cap on that. But if you can close it by putting additional caps, but usually this is what we have. Of course, you can also create that effect by how, what would, instead of a simple straight angle line, how this line should be.
So you're talking about closing the
Yeah,
cylinder?
close the top also without putting an explicit cap. Like you, this was generated by the following, right? You have a, okay, I have in the other screen, I'll try that. Okay, I don't have this. So here, if you have, you take an angled line like this and then I rotate it, then the cap became open on that. If you want to close it, how do you do that? You
So
can
instead
take
of
something like a U-shaped line, which is little different on the lens, and then you can rotate it. You can still get a closed cone, correct? That is also possible. Are you guys able to imagine that? Okay, maybe I'll show when I come back to the other thing. So we don't usually have a top cap and a bottom cap, of course, and in this case, you can see there is a change in the, again, you can do whatever you want, and your cone, becomes very different. All that thing changes everything you can make, and you can see a double cone. All those things will be interesting. So if you guys know how to handle these things, you can create quite a new kind of surfaces on that. Okay, so this is a cone, and so you can think of cylinders. Of course, you have a torus, so you can see a torus coming in. So how do you create this torus? So how do you create this torus?
By rotating a circle.
By rotating a
and
circle.
then-
Yes, correct. So by rotating a circle, you can create a torus on that. So you can have minus radius, all that thing. So if you change it, you will get, of course, different sizes and so on. So you can create a lot of, sorry, if you just go to the app or, GUIRIT or GUIRIT, you can create different surfaces and then see how you can manipulate them and and so on. So this is one of the things where you can study some of the surfaces and you can go and look at a lot of other surfaces and so. Okay, so this is surface of revolution is a very important topic in that. So I'll just go to the other screen now. So if I'll just go back to my other point that I was telling. So how do you create this closed one? So what I was hinting at is that, so if you put only a line like this and then rotate, both sides are going to be open, correct? So instead of that, you put something like this, a line segment, something like this, maybe in a different color. Then if you rotate it, what will happen? This guy, if you rotate it, what will happen on this?
Closed cone.
So it will be closed on either sides, correct? So you can choose your curve in such a way you can get this closed shape without explicitly needing to close at the top. Okay, that's what my point is on that. Okay, so you can do something different on that. You can create a lot of nice shapes on this. Okay, excellent shapes that you can try, and I'll probably show when we go back to that. Okay, so this is one of the other surfaces, very important one. And then we'll go to Bezier and B-spline, hopefully. So bilinear surface is basically, you can see that you take 4 points and you do linear interpolation on both of them. Like for example, you have P00, P10, point P10, and you go to a bilinear interpolation between these 2 points, you go to this point. Okay, and in a similar way, use the same parameter, whatever, let's say if it is U, use the same parameter at the top, use these 2 points, and again go to this point. Okay. Now you have in U direction, use those 2 top points and bottom points, and you have these 2 points. So you go in W direction now, and then you do again another linear interpolation between these 2 points. Let's say you have P and okay, maybe another letter. So you have another point, let's say Q1 and Q2 from the other side. Then you linearly interpolate between these 2 points and you go to U comma W. So this is a W direction in this side and this is a U direction. So remember that you are using linear interpolations on both parametric directions, and then you can go to any point on the Q of U comma W. So what this surface will look like. Suppose if you take all U's and all W's, how will the surface look like? Are you guys there?
A plane.
Okay. So when it will be a plane? Okay, suppose if out of 4 points that you have from which you are doing successive linear interpolation, suppose if one of them is out of the plane of the other 3 points, so what will happen? So how that surface will be?
Will it like jump through that point?
No jumping. We are just instead of for all 4 points lying on a plane, when you do this interpolation, let's say I say one of them is out of plane of the other 3. Of course, you need a 3 points to define that plane. So let's say the 4th point P11 is out of the plane of other 3 points. So can you do the linear interpolation of that or not?
We'll get a prism.
Why prism? We are not closing it anywhere, right?
Okay.
So will that surface have planar like behavior, or will that surface have some curvature, or how do you think that the shape of the surface would be? Because we are using linear interpolation on either side. Okay, so some confusion.
So two joint triangles.
Correct. In a sense, you are right. But will it be two triangles joined, or will it become something different? Okay. So that's a little difficult to see. I'm showing a picture here. You can see you can get a very highly curved surface. Remember these two guys, these 3 points are on one plane. Let's say P00, 10, and 11. And then P01 is somewhere. Now you can see the shape of the object here. Are you guys seeing the screen? So you can
Yes,
see
sir.
these 3 points are on a plane, and this point alone is some out of plane on that. Okay. Now you can see that, okay, how this surface looks. So did you guys imagine something like that or no?
Not exactly.
So little difficult. So this surface, interestingly, is called hyperbolic paraboloid. So you can see a very simple idea of pulling one of the 4 points out of plane. And remember, you are only doing linear interpolation. You are not doing anything more than that. So you are doing linear interpolation on either side of the parameters U and W or U and V or whatever you want to call. But you can see that it ended up in a highly curved surface. So this is what is called as the hyperbolic parabola. Okay. So maybe let me just show quickly on the other screen before I come to this. Okay, suppose I guess you are able to see this now. and I'm clicking this. Are you guys seeing this surface? See how it is? He kind of told it's two triangles, somewhat correct or somewhat intuitively, but you can see how curved this surface is. Of course, in this case, 2 points are out of plane, and then you can change maybe one of them to be something like this, and you can still see how that curvature is. So you can get a very highly curved surface by just the linear interpolation. Okay, so I can just move these things and you can see how the object is. See, remember it's only linear interpolation. I'm not doing anything more than that. You can see highly curved surfaces I can obtain. Okay, so this is a simple linear interpolation on both parametric directions. So did you guys observe that? Can you say something, please? Yes or no?
Yes, sir.
Okay, that's
Yes,
good.
sir.
Because I'm switching between these two, and so this is very simple linear interpolation, and you see that you can get a really high surface by a simple technique. Okay, and you just do linear interpolation on either side, and that is all. Very simple procedure, and you will get a parametric surface, which is called a hyperbolic paraboloid. Okay, so that is the greatness of using these parametric models